In the next few videos, we want to talk about end behavior or behavior at infinity. So we're going to start off by looking at end behavior of polynomial functions, but I want to discuss the idea in general first. So when we talk about infinite limits at infinity versus having a limit at infinity versus no limit at infinity, these are three different types of what we call end behavior. Let's draw a set of axes to indicate the first situation we were talking about. And that first situation that I'm addressing right now, that's this infinite limits situation. So when we look at that infinite limit situation, what we're really saying is maybe when you go off to positive infinity, the x values go off to positive infinity, then your function might explode up to positive infinity like this. Or as your function goes towards negative infinity, maybe your function also goes down to negative infinity like this. So in this type of situation, I would say we have infinite limits at infinity. You go to positive infinity and your function just gets bigger and bigger and bigger. You could also get smaller and smaller and smaller in a negative sense. That would still count as an infinite limit. Same thing when we go to negative infinity. Maybe it goes down to negative infinity like this, or maybe it comes up to positive infinity like this. Either way, that's what we call an infinite limit. Having a limit at infinity, what does that look like? So when you have a limit at infinity, let me draw a picture to help you understand. So I'm going to draw a set of axes like this. Okay. And let's put our function in blue. Let's say as you get closer and closer to infinity, um, you know, we might have a horizontal asymptote like this. So as you get closer and closer to positive infinity, maybe your function looks like this. And this line is y is equal to L. Okay. Or maybe when you go towards negative infinity, your function starts to hug the line like that. In both situations over here, this is saying that your function has a limit at infinity. It's going to some sort of horizontal asymptote. So this is sort of like the horizontal asymptote case. All right. And then what would the third situation be? The third situation would be something where, you know, maybe let's draw a set of axes first like this. And then for an example of the no limit at infinity case, no limit at infinity, a good example for this is the sine curve. So if I drew the sine curve, the sine curve just keeps oscillating back and forth. This guy oscillates back and forth like this. Okay. So this situation is different from the previous two situations, right? In the first situation, the the y values exploded off to infinity or negative infinity. In the second situation, we went towards a number. But in the third situation, the limit doesn't exist. It just keeps oscillating back and forth between -1 and 1. Okay, so so this third situation, you have no limit exists. In the second situation, you had a horizontal asymptote. And in the first situation, we would say the limit as x goes to infinity of f of x is equal to plus or minus infinity, and the limit as x goes to negative infinity of f of x is plus or minus infinity. So these are the sort of different types of end behavior that we could have in general. What I want to do next is I want to focus on the end behavior of polynomial functions. So when we're looking at polynomial functions, we can really determine the end behavior or the behavior at infinity of a polynomial function by looking at the leading term. The leading term, you could also think of this as the highest power. Okay, so really studying end behavior of a polynomial function is really looking at leading terms. And leading terms is really just, what we call power functions. So let me draw a couple graphs to illustrate the two main flavors we're going to have. So let me draw a couple set of axes to help you understand the picture. This is one set, and this is the other set. And the first case is going to be the case of the power function x to the n, but n is even. So we know that when we have even power functions, your curve kind of looks like some sort of a U. The second situation is when you have x to the n, but n is odd, then your function is going to look more like this. I call it a John Travolta graph if you've seen Saturday Night Live, but it's kind of like this. It's like a person sticking their left arm up in the air and their right arm down to the ground. Okay, so these are the basic graphs we have for our power functions. So again, understanding n behavioral polynomial, just look at the biggest power. So let's take a look at an example where we look at the biggest power. So in example 2, you see we have this negative 5x cubed. And the important part I want to emphasize here is that negative part. That negative is going to give me this is a vertical reflection. Okay, so my graph of this guy actually looks like this. I draw the axes. I'm going to have a flipped graph, so my graph is actually going to look like this. And the 5 in front, the 5 is a vertical stretch. So that's not going to affect the behavior at infinity, just stretching it out a little bit. But the sign in front makes a big difference. So what could I say? I could say as x goes to positive infinity, my function f of x goes to negative infinity. We can see that just with this picture. As you go further and further to the right, the function seems to be going down. Okay. Of course, the mathy way we would write this is we could also write it as the limit as x goes to positive infinity of f of x is equal to negative infinity. So I kind of like to write it both ways, but this is the way that we probably use more in this class. I could do the same thing as I go to negative infinity. The limit as x goes to negative infinity of f of x is going to be equal to positive infinity, right? Take a look. As I move further and further to the left on the graph, my function's getting bigger and bigger. All right, let's look at one more example. When I look at g of x, I see there's a 2 in front here. That 2 is nothing more than a vertical stretch. A vertical stretch is not going to affect the end behavior. All right, so when I draw my picture this time, draw my axes like this. X to the fourth is an even powered power function. So this guy kind of comes up like this and comes up like this. So as we can see in this case, the limit as x goes to positive infinity of g of x is just positive infinity, right? As we move further and further to the right, the function gets bigger and bigger. Same thing, if I go to calculate the limit as x goes to negative infinity of g of x, and that's going to be equal to positive infinity again. As I move further and further on the right, my function gets bigger and bigger. All right, folks, that's it for this video. Take care.